Hey folks, so in this lecture I want to talk about a very specific scenario for elastic collisions. So elastic collisions are collisions in which I don't have any change in total kinetic energy of the system. So I need to consider both objects. Their total sum of kinetic energy does not change in the system. So in my notes, I actually go through a derivation of this exact scenario in detail. I didn't want to put that in here right now because you're just following me doing some algebra, a little bit of substitution from one equation to the next. I'm going to leave that up to you. If you are interested in understanding where we get these expressions from, you can look at that in my notes. But for now, what I want to talk about is setting up the scenario, talking about the expressions, and then talking about the results. So the scenario is that I have one object coming in with some initial speed, and it has some mass, and there's a second object, call it M2, that has no initial speed. It is at rest. And so when this initial object comes in, it's going to hit the object at rest, and then they will collide and transfer some momentum. I'm hesitant to say that they'll both move because there is a very specific scenario in which they don't. But by and large, M1 and M2 will then collide and both begin to move. Now, what we can do is basically set up our equations of delta KE equals 0 and delta P equals 0, substitute together, and with this constraint that the initial velocity of mass 2 is 0, we're able to simplify into a really nice expression. So the big question here is, what are the speeds of mass 1 and mass 2 after the collision? This assumes that we know the initial speed of mass 1 coming into the collision. So again, very specific scenario. Mass 2 cannot be moving. Mass 1, we know the speed. And of course, we need to know the masses of both of these objects. But if we satisfy all of those conditions, what we can then say is that V1F is equal to M1 minus M2 over the sum of M1 plus M2 times V1I. Now you're probably going, where in the heck did you get that expression from? Again, it's in the notes. I didn't really feel like going through in detail doing every little algebraic step out to show how we got this. But this is one of our expressions. The other expression is V2F. V2F is equal to 2M1 over the sum of M1 plus M2 times V1I. So these are two really condensed and really useful expressions to find the final velocities of the balls, of the objects in play. Now, what's really interesting is when we look at very specific scenarios. There are namely three scenarios that I want to talk about. And the first scenario has M1 greater than M2. So I'm saying that M1 is a big old ball. M2 is a very small sphere. M1 is going to come in and hit M2. Now, M2 is going to move, right? If we look at our M2 expression, M2 will always move forward in the direction that M1 was coming in at. M1, though, M1 has a couple different options it can do. Now, if M1 is greater than M2, I'm going to continue in that direction. I'm going to actually keep plowing through. Now I hit M2, and it's going to move faster than M1, but M1 is still going to move in that direction. The second scenario is that M2 or M1 is less than M2. So M2 is the big sphere, M1 is the tiny little sphere. As M1 comes in, of course, M2 is going to move in the direction that M1 was coming in at. M1, though, since it's smaller than M2, it's actually going to move backwards. It's going to have a negative velocity, a negative final velocity, which means we're going to move backwards. We're going to move in the direction that we came in at, from the direction we came in at, not in the same direction we were going. So we have kind of these different scenarios here, and if you're really paying attention, you might be wondering, wait a second, what about M1 equals M2? What if they have the exact same mass? If they have the exact same mass, M1 is going to come in, it's going to hit M2, M2 is going to move. But if we look at our expression for V1F, M1 is going to stay put. It perfectly transfers all of its kinetic energy and momentum to mass 2, M2. So these are the three different scenarios that we have here for this very specific. This is not a general situation. It's a very specific situation of an elastic collision. We're going to find out that it's very useful to use for a couple problems. So again, if you're interested into how we got these expressions, look at my notes online. But hopefully this was illuminating as to how the relationship of M1 and M2 actually affect the dynamics of the system, right? How it affects the collision and the output of the collision of the system. All right. If you have any questions with this, feel free to contact me via email or pop into an office hour. I'm happy to talk about this. All right. Have a good one. I'll see you later.